Zoom in out.
Okay, fine. Yes.
Check. Hello. So I think that's a great talk to lead into this one because I happen to be a Emacs user myself, and this presentation is actually a LaTeX source that was created in Emacs. I actually wanted to present in org mode using org present, but in the last minute I decided to go old school, like completely old school, and do a LaTeX presentation. Welcome to this talk. I purposely titled it very weirdly called "Free Yourself with Constraints." It's supposed to be a play on this phrase "free yourself from constraints." So people usually find constraints to be like, "Oh my God, I'm constrained. I can't do a lot of things." So it's like you add more constraints, you are free. So it's a play on that phrase, like "free yourself with constraints." Yeah. So a bit about me, I have a total of about 7 years of experience in software development. Most of that is in the Java and Spring stack, which is what I primarily worked on before I joined ThoughtWorks. After I joined ThoughtWorks also, a lot of it has been in the Java Spring stack, but I have recently gotten an opportunity to work with Scala thanks to a big data project. I was bitten by the FP bug in 2012 thanks to Scala. I think I was searching for what Twitter used in their tech stack, and that is how we came about Scala, I think. And I have fallen in love with it ever since. If you talk to people I know here, or if you find me roaming the streets of ThoughtWorks, people will tell you that I have an affinity for functional programming and type theory. You can find me talking about it a lot. And because of these interests, I also occasionally dabble with languages like Haskell, Litris, and PureScript. These are mostly for pet projects, nothing in production, but they are like indicative of my interests. And if you have not seen the index or slide index on top, or if you have not gotten an idea, I think this should give you an idea of what this presentation could be, even though I titled it weirdly. So, agenda for the day. I'm going to start with some introduction, which is, I guess, what we're doing right now. I'll establish some ground rules just so we don't end up discussing things we don't really want to discuss. Because this is obviously going to be a talk on functional programming, we will look at some of the constraints that FP already imposes on us by default, by its very definition. We'll look at why they aren't enough, what can be done about it, and hopefully reach some sort of a conclusion. Just some ground rules. I put this slide because whenever people talk of, so first of all, to begin with, how many of you have done functional programming or familiar with functional programming here? A bit. Yeah, we have a few people. So this always comes up when people talk of functional programming. There's on the one side you have people like me who say that it must be very easy to read my code, understand my code, and reason about my code. Whereas on the other hand, if some set of people are saying that it makes my code slow, it creates a lot of garbage collection or stuff like that. So this is just some ground rules for this talk. We are not going to be talking about performance here. So a lot of the concepts I am going to be talking about, we'll talk about whether they help us with these three properties, whether they help us understand our code better, whether they aid in readability, and hopefully help us reuse some existing code. We're not going to be talking about performance. It's just some ground rules so that we don't end up discussing things we don't really want to discuss, or is not really the point of this presentation. So moving on. So constraints already imposed by FP. Pure functions, I think it's fairly obvious. The name functional programming tells us that we have to only write pure functions in our code. So this is different as opposed to your regular imperative style of programming, where your program is more a series of instructions that gets executed. You say, this is my first instruction, this is my second instruction. Whereas here it's more like this is the function, this calls this function, this calls this function, this calls this function, and your program reads like a series of function compositions rather than instruction executions, so to speak. So that is the number one constraint that FP already imposes on us, is that we should only be writing functions. And this other thing is immutability. So how many of you is familiar with the term immutability? Fan number. So all it states is that any function that we write cannot modify global mutable state. It cannot modify global variables anywhere. It cannot throw errors. It basically do anything useful, so to speak. So these are constraints already imposed by FP. So how many of you think that this is already limiting me too much to express? How many of you think that this is already too constraining, so to speak? Hopefully no one. So why are they necessary? If you just give it some thought, you can't do anything useful in your functions, which is like mutate state globally or something like that, and you have to just write pure functions. So why are they necessary? So for me, if you ask me, I would tell you that these are the bare minimum constraints we should be working with: immutability and pure functions. And remember that you can do this in any language. You don't necessarily need a functional language to do it. You can go tomorrow and start doing this in Java, C, even in your regular imperative languages. So why are they necessary? So primarily referential transparency. How many of you is familiar with this term, referential transparency? So what it states is that the function, any function that you write must produce the same output given the same values. So you write a function, takes two arguments, it must do something useful to those arguments and return a value. And given the same set of inputs, if I call a function with the same input, it must always return the same output. That is all this property states. So this property of referential transparency gives us some benefits, which is what we like to call equational reasoning. So when we try to reason about programs by replacing the calls to external functions with the values they produce. So if you think about it, this is what we did in our high school mathematics. When we tried to decompose quadratic equations or these huge equations that made no sense to us, what we did was, okay, this is what this equation represents. This reduces down to something, the sum value, and that reduces down to something. And we reasoned about them as equations, basically. What is the value produced is equal to this expression. So we would like to do the same thing to our programs, and that is what referential transparency gives us, because there is no mutation of global state going on, and because it always gives the same output given the same input values, we are able to do this. We are able to equationally reason about our code. And this is just something that I believe both of these properties really helps us with refactoring. Because when we are trying to understand code, more often than not, when we are refactoring an existing piece of code, we are really trying to understand what it is doing so that we can change the behavior in some way. Because these two properties help us understand what the existing piece of code is doing, it really aids us in refactoring also. And any breakage is immediately visible because you have only pure functions going on. And if you change something in some way, the value that gets returned changes. So things immediately start breaking. So these are, I would say, FP, those two properties that we saw in the previous slide are the bare minimum constraints we should ideally try to work with given any language. And this is the benefit that it buys us. So then why are we standing here and saying that is not enough? I'd like to think that it helps us, it makes it easier to think when you look at some examples. So we'll just take a few examples. So let's take a very simple function. This is obviously written in JavaScript. Can anyone tell me what this function does just by looking at it? Just by looking at this.
Adding to it.
Yeah, exactly. It's a very safe assumption to make, I would say. How did we do this? Name inference. We obviously looked at the name of the function. It said add. We looked at, okay, it took two arguments. And we also applied some general experience and common sense. We have all worked with enough programs in our lives to know that, okay, somebody's named the function add, it takes two arguments. It is going to return the sum of those two arguments. It's just common sense, right? But wait. So before you all kill me, this is a very, very trivial example, I agree. Nobody's going to name their function add and convert the variables to string and append them together. But To give you a larger context, this is example of code we would come across on a day-to-day basis. And the reason is, as programmers, we are terrible at naming things. Absolutely. In fact, we are so bad at naming things, we have a long-running joke about naming things that has passed through decade after decade. Generation after generation of programs have a joke about naming things. So this happens a lot because we are bad at naming things. When we try to look at names and reason about code, okay, this person has named this function something, it obviously has to do what it says. It will never work for reasons we already discussed. There is always a necessity to look under the covers. We have to go into that function block to see what it does, to really feel comfortable about, okay, I'm using this block of code, it says yes, okay, it really actually does X. Right? This is just other forms of reasoning can and will fail at some point. What you saw in the previous slide was a trivial example. You may find it funny, but I have worked in larger blocks of code with tremendous business logic where I have faced this problem, where I tried to reason about it by looking at some names and it failed. There is simply not enough information for the reader, right? We could try to infer things based on names, but beyond that, there is not enough information. Obviously, JS is a dynamically typed language, where A could be anything, where B could be anything. They could do anything they want within that block of code. They could return 0, they could return 1, they could return A, they could return B, they could do whatever they want, and we would be none the wiser. There is too much power to the implementer. So the person who wrote that block of function code, they have too much power. They can do anything they want basically. And we'll just take a look at this last point as we segue into the next section. How somebody said it adds two numbers, right? How did we do it when we looked at that block of code? So when we saw that, we mentally constrained the values for input, right? In our head, there was a constraint. In our head, we thought, okay, A has to be an integer, B has to be an integer. That was not apparent in the code, but in our head, we still had that constraint. We were thinking about these constraints in our head, which nicely then brings up to the next section, which is what needs to be done. And obviously, since at the start of the presentation, I said I'm a fan of type theory, we obviously look to types to the rescue. So can you guess what this function does as we're looking at it? Anyone?
So ends and returns and ends.
Yeah. We're getting better. We're saying returns an int instead of saying it returns the sum of A and B. So this is much better, I would say, because function takes two integers and it returns an integer. The mental constraints we saw in our earlier slide, right? We implicitly assumed that okay, A and B had to be integers. They've just been made explicit thanks to the power of types. So is it safe to assume this function does what it says?
Depends what you read, what it says.
No, just look at it and what it says. Obviously not. So like we said, it returns an integer, right? That could be any integer. Again, this is a very, very trivial example. Nobody's going to name their function add and do A minus B there. But even when you are working with languages that have pretty decent types, Java, Scala, or whatever, this is something you come across on a day-to-day basis. Even I do. And again, types alone aren't enough. Although types help us reason about our code slightly better because we have made some mental constraints explicit, they're still not enough because just like in this example, they still give too much power to the implementer. The implementer knows too much about what they need to do. So in the case they need to return an integer, they could choose to return 0, they could choose to return 1, they could choose to return A minus B, A multiplied by B. They could choose to do a lot of things that we wouldn't know about without looking under the covers. And as a reader, like I said, we just don't have enough information. We'll have to look at what they actually do within that block of code to really feel safe. Okay, I can look at this and I can assume they do what they say. So what is the answer? We've just seen types alone aren't enough, which brings us to parameters. How many of you have worked with generics, parametric polymorphism? That's a fab number. Good. So this is a very famous paper written by Philip Wadler. Philip Wadler is one of the lead designers of the Haskell programming language. He wrote in 1989 this paper called Theorems for Free, which is basically about parametric polymorphism. That what he says is, Write down the definition of a polymorphic function on a piece of paper. Tell me its type, but be careful not to let me see the function's definition. I will tell you a theorem that the function satisfies. The purpose of this paper is to explain the trick. It is a very terrific paper which takes this concept of parametricity or parametric polymorphism and proves mathematical theorems about well-known functions, like functions we would have used on a day-to-day basis, like map, fold. Philip Wadler proves theorems about them, mathematical theorems that can never be false. It's a great paper, but it's also highly rigorous and mathematical. I went through it once and couldn't really understand it fully. It's still nice to give you a sense of what parametricity is all about. So we'll take a very simple example. Let's take a simple parametrically polymorphic function. Can you guess what this function does just by looking at it? First of all, how many useful things can this function do? It can do a very limited number of useful things. How many useful things can it do? It's a single digit number. Hang on. You can do just two useful things. So what are those useful things? You can either return A or it can return B. First, before somebody who knows Scala jumps on me, Scala is a fundamentally unsound language, so they can still return null, they can do some casting, they can throw exceptions. But just for the purpose of reasoning, we'll assume that you can't do those unsafe things in Scala, or that Scala didn't support those things, and assume that you can do two useful things. I think it's safe bet to say that in most other languages, but Scala has other issues, which we won't talk about. So, why were we able to do this? That is the power of parametric polymorphism. So when you look at this block of code, you know it does a few things. You know it is parameterized by some type A, and it takes two values of that type A and returns a value of type A. But the implementer does not know what A is. A could be anything. A could be integer. A could be string. The implementer has no knowledge of what A is. It gets its knowledge when we call it. When we call do something with an integer, A becomes an integer. When we call do something with two strings, A becomes a string. When we call do something with two person types, A becomes a person. But the implementer has no knowledge of that. So all the implementer knows is I have to return a value of type A. And within the scope of this function, they have only two values of type A they can work with. They have either A or they have B. So that is all they can do. Within the body of this function, they can either return A or they can return B. That's all they can do by the benefit of parametricity. They can't do anything else, basically. So there is very little power for the implementer. If I write a function like this, I would be very constrained. What can I do? I know what I have to do. I just have to do two things. And there is lots of info available to the reader from the very definition. So when I look at this block of code as a reader, I know that within this block of code, they can either return A or they can return B. So I have to call it once to know what it does. It will either return A or it will return B. And for the next infinite times, I can use this function safely in the knowledge that it will always return A. Given any two values, the first value will be returned or the second value will be returned. And I can do that safely because of parametric polymorphism. Does everybody get that? Is it clear? So let's take another familiar parametrically polymorphic function. I have named this something, do something else. Sorry, yeah.
Thing is that actually previously you showed the example of integer.
Yeah.
So what difference does that make with the part? Because you finally know that you are going to return.
Yeah. In this case, they know they have to return int. Yeah. So within this block of code, like we just saw, they could do A minus B because A minus B is a valid integer. The compiler will not complain. They can return A. A would be a valid integer. B would be a valid integer.
That's not also possible with the parameter.
No, it is not possible because They just know it is some A. They don't know what A it is. So they don't have access to any of the functions within A, because A can be any A. They can't do A dot, they can't call a function. They can't call a function B dot or something like that. They can't do that because they just don't have enough information about what A is. They just know that they have to return a value of type A. It can be either A or it can be B. They can't do A plus B, they can't do A minus B. They can't invent a value of type A out of thin air because they don't know what A is.
That thing is fine because it again contradicts with the scope of the function. If he is going completely out of
Sorry?
no, he is going completely out of he is getting some value out of A.
Yeah, that contradicts with the scope of the function. Nobody is going to disagree. But they can still do it, is the point. There is not enough constraint on them. Like I said in the add example, nobody is going to name their function add and do A minus B. But think of a large business logic. And you could, when you have too much information about the values you're getting, you can do millions of different things, do different things to them and do something unsafe. These are very trivial examples, but think of them in larger contexts, right, where this could be useful. Even a very simple example, we see the power of parametricity. Whereas in the add example, I agree, it's very trivial. Nobody's going to do it. But even in this simple example, we know that because of parametricity, they can do a very limited number of things. I think that's sort of the point we're trying to get at. Yeah. Moving on. So I have named this do something else just to make it sound weird, but just by looking at the type, how many of you know what the real name of this function is?
For any given types A and B, take a list of A and a function that transforms A to B and return a list of B. So basically transform.
Yeah, map. Map is. So what would it do?
Take the list of A, for each element of A, transform it to B and return a list of B.
Exactly. But again, a very trivial example. But nobody is going to do this in the real world. Please don't eat me for it. These are all just examples to prove a point, to show you the power that we are getting. So nobody is going to just take the first element of the list, apply F to it, and trap it in a list and return it. But again, there are problems here. And the problems is parametric polymorphism alone isn't enough. In a case like this, the implementer still has too much power to work with. They know list, right? So list has many functions defined in the class. So they can still call any of those functions, apply F to it and return it, and it would be valid. It would pass the type checker. The only time it would fail is when we try to call this API, something would blow up. Okay, what blew up? So implementer still has too much info to work with. There are cases. So parametricity is a great concept, but when we are working with higher order types like this, there are cases where the reader still has to look under the covers to really feel safe. But okay, this API does what it says. Which I think nicely brings up to the final section of the presentation. So how many of you are first of all familiar with this notion of type classes or higher kinded types? Wait, we have a couple. So I am going to be moving slightly faster in this section of the presentation because, to be honest, type classes requires an entire presentation on its own. It's a very, very huge topic. Multiple papers have been written about it. We'll just, I hope to give you all an intuitive sense of the power that we get with type classes and higher kinded types. If you have difficulty with the specific syntax or something like that, you can hit me up later. We can have a discussion about it. Let's try to get an intuitive sense of the sort of power we are aiming for when we discuss these two concepts. So yeah, this is a very simple block of code. All we are saying is this is a trait. So if you're new to Scala, you can think of a trait as an interface, normal interface. We're saying that this trait's name is functor and it takes a parametrically polymorphic type. But the key difference is here f of underscore denotes a higher kind of type. So whereas list of A could be any A. It could be a list of integer, it could be a list of string, it could be a list of person or whatever. That is what the A indicated. Here what it says is it could be any f, but that f itself has to be a higher order type. That f itself has to take another type to become a fully formed type. So here f could be a list because list is not a fully formed type. You just can't say list and it be valid. You have to say a list of integers or a list of strings. So the list type itself takes another type to become a fully formed type. So in Functor, what we are saying is, give me some of these types. Give me a type that itself has to take another type to become a fully formed type. It's sort of confusing, but you can think of them as analogous to higher order functions. So that is where this term higher kind of comes from. So when you say higher order function, you refer to functions that themselves take functions, right? Here when we say higher kind of types, we refer to types that themselves take other types to become fully formed types. So try to sort of get an intuitive understanding of it. So the functor type class, what it says is, I have this map method, and the map method is completely polymorphic. What the map method says is, give me any A, give me any B, give me an FA and a function from A to B, I'll give you back an FB. So what the functor type class does is, it is parameterized over this higher kind of type F, and it specifies a contract. What that contract states is, anything that wants to be a functor must implement this map method. That's all it states. So why are these two concepts beneficial? And how does it sort of tie back into this notion of constraints that we have been discussing? So instances that are, when you work with type classes, this functor type class, you define instances for, we'll see an example in the next slide of what I mean by instances, but you define instances for this type class for each F, for each parametric type that you're working with. In this case, F could be a list option, or basically any type that requires another type.
Is it more like an interface?
It is an interface, but it can't be extended. We'll see an example of the difference. You implement an interface, but here the contract is slightly different.
Like a type wrapper, something like that.
And it's fully parametric. If you think of interfaces, when you say interface person, there is no real parametricity going on. You just say some functions, anything that wants to be a person.
You can still have an interface.
Yeah, you can still do that.
Interface, you can have another interface which has a parameter.
Yeah. But here, we'll look at it in the next slide. See, these instances are distinct entities. Again, some examples in the next slide. So, if you're still having difficulty understanding higher kind of types, you can think of them as higher order functions. HOFs give you the power to abstract over functions types. HKTs, higher kind of types, give you the ability to abstract over the type constructor itself. Basically, instead of saying this is a functor of list, we're saying this is a functor of some F. That F could be list option. Just if you're having difficulty. That has numerous benefits in practice, primarily when it comes to reusability. We'll see some examples. So what we mean by different instances. So implicit object. So this is again some Scala syntax. We're saying list functor extends functor of list. So we're saying list functor is a functor of list for this list type. And this is how it implements the map method. And what we're just doing is calling the lists map method. That's all we are doing. Because we have a map method defined in list, list can be something that is mapped over. You're saying this list functor does this map method by just calling the list map method. It's very simple. The same for option. We'll see why this is better. You could ask the same thing. What if they had done the same erroneous code within list? That would still fail. Yeah, but we'll see why that is not the case. So the difference between this and interfaces, you define an interface, you have a class that extends that interface, and you have when you create new instances for that class basically. But here this is all that. You can't create an instance of list functor. This is the only instance of list functor that will exist anywhere in your application. And this is how it will always do the map function. I think that is the key difference. That is just one instance. So there is just one instance of list functor in your entire application. And this is that instance. You can't say new list functor and do something with it.
So what's the advantage?
So there's only one instance of each class, each instance of one instance of list or option for our entire application. So I'll show you some code that will hopefully make things clearer. We'll see some actual samples But to the question of how is this safer, the list implementer could still have implemented map in a fundamentally unsound way, like we just saw a few slides back. So you can write property-based tests in Scala. So I can say that anything that wants to be a functor has to adhere to these properties, and that is independent of what the thing is that wants to be a functor. That is independent of list or option or any other thing. And whenever we create new instances for this functor, those properties are verified. So in the case of functor, it's actually it's a concept that comes from a branch of mathematics called category theory. So you have these mathematical laws about it that you can encode as property tests. But the key thing is you can do this for any of your instances, any of your type classes also. But they can't do anything unsound within the list implementation, because then the property test would fail. I could ask, okay, I could write unit tests for list, but that would be specific for list. Here it is not specific to list, it is not specific to option, it is not specific to any other type. It is very generic by the definition of parametricity. So, yeah, reusability. So given this trait functor f and this implementation of map, I want to define a lift function. And that basically is, given any function from a to b, I will give you back a function from fa to fb. So there is only, given these constraints within this slide, there is only one valid implementation for this method. And that is, it's just an anonymous function that says, given an fa, I'll call map with that fa and that function, right? So this is just some reusability, but I'll just show you some code of what I mean when I say this is reusable.
So you spoke about property testing, right?
Yeah.
So is there anything that is analogous in Hoops code? See, because I'm basically a Hoops programmer, so I cannot come into that.
Yeah, I don't think there is an equivalent, because when you write unit tests, right? Again, property-based testing is an entire topic on its own that requires an entire presentation. But when you write unit tests, you say this is the value I'll give to this function or this method. This is the output that exit will assert on that. When we say property-based test, you will give some property of that function. Let's say append function for lists. It's a very, very classic example. If you want to append two lists together, the output should be the length of the output list should be the length of sum of the lengths of the two lists. This is a property that will hold true for any list of any two lengths.
Just add to that. Just add to what you say.
Okay.
No.
So the property-based testing actually means that you're writing tests for the invariants in your code. That's the prime focus of that. And exploratory testing and the idea of quick check and all that is that you actually generate tests, you don't actually write tests.
So you are trying to put a data contract, basically a contract on the implementation.
Yes. That's what he means by property. The CS term is invariants.
Okay.
I don't know how it works in Oops.
I don't know. I don't think so. Is there?
No, it's not there. It's there in F sharp. There's a library called FScheck.
Even for JUnit, you have JUnit quick check, something like that. So it is like your unit tests are like examples. You just give examples.
Yeah.
So these are like hypotheses. You try to say like what's its behavior. You don't give examples, right? When you give examples, you tend to miss edge cases. When you go give a hypothesis, it generates like thousands of possibilities, which helps you discover your flaws.
Yeah, basically in the list append example, it would create thousand different cases of list. There will be something called generators. Will create 1,000 different values of list. It will try to append them, and it will try to see whether this property that you described holds, which is the length of the appended list should be the length of the input list. For list append, it may hold. It is in practice, it is kind of difficult to write property tests. You really have to think a lot, and you have to structure your functions in a way where you can describe properties about them. It is kind of difficult to do this when you're working with OO programs. By definition, I think parametricity does help here because it makes you think of generic properties of your functions.
It is easier and
It is easier with parametricity. You can do this in Java. There's a library called functional Java that lets you do it. but you must at least be working with parametricity. Otherwise, it's very difficult for us to say generic properties about our
So
functions.
you cannot compare this with unit test, right? Unit test is
It is wildly different. And like I said, it generates test cases. That's the key difference. Here we write our test cases. Yeah, that's a whole other topic. Maybe we'll have a presentation about it in the future. So this is the same code that we saw. We define a functor. We write, say, this contract of a map method, and we define the lift in terms of map. Just to give you a little example of what kind of reusability we get with type classes and higher kind of types. Then we define two functor instances for it, which is what it does. This is what a functor of list does, and this is what a functor of option does. So I have just defined this function called reuse, which takes a function of int to double, and it also takes any f. It could be any f there. It takes an implicit functor instance for that f. So that is what this is saying. It's saying at compile time. Oops, sorry. At compile time, try to find whether this f, and that f could be list, that f could be option, that f could be any other thing, whether it has a functor instance, which is what we defined a few lines back. This one. This is a functor of option. So when you say functor of f, and that f happens to be at a function call time, if it happens to be an option, it will try to find a functor of option. If it can't find it, it will fail at compile time itself. So there is no dynamic dispatch going on, there's no typecasting going on, it's all at compile time. You get all the safety. And an example below. So what I have just done here is, what I'm saying is this is just a functor of some variable name f list. I call reuse and parameter reset by saying this is going to be reuse of list basically. And I just give it some function. It takes an integer and converts to a double, which is what the type signature says. The type signature says my f should be something that takes an int and gives me back a double. And this is what it does here. But the key thing is, here, when it comes to this line, list functor should be in scope. That is what that import does, basically import functors. So if I either remove the import or say do this, right? It will fail the compiler. It will say I can't find a functor of list. You said when I call reuse with some type list, I need to find a functor of list. That is what you've said in your definition. I can't find one basically. That is what the compiler is crying. So when I put it back in, work. Yeah. So the key thing we want to talk about is constraints again. So within this straight functor f, we are extremely constrained. We don't know what f is, we don't know what a is. We can't do anything other than work with those things here. So when I define this lift function, right, all I have in my hand are this f and this that function a to b and this notion that I have to return an fa to fb. And the reason I am able to write this lift method in terms of map is the types aligned, right? It takes I'm just creating some anonymous function that takes an fa and calls map with that fa, and that map by its type returns me back an fb. Again, that f could be list, that f could be option, that f could be anything that we defined that the functor type class does not even know about. So when the functor type class is written, it need not even know about some type in the future that I create that that can be mapped over like this. So to give you a very simple example of why say type classes are beneficial before sort of someone asks me a question. So let's take a very simple example. You want to serialize some data. So in your classic overworld, you have say some library that has an interface called serializable with some serialized method. Say interface serializable, this is the contract. Anything that wants to be serializable must have a serializable method and it must tell how it should be serialized. So in some other library, you have a value object. Any value object, let's say it's a person, for example. Now person does not implement serializable because it's some third-party library which we don't have access to. So if I want to serialize person, what would I do? I can't. So we know that person has to implement serializable because that's the contract of serializable, but we can't do that because we don't have access to the code base where the person value object is defined. You could create a new class that extends person and implements serializable wrapper class. This is what we end up doing, but it has some downsides, obviously. Whereas in this case, just to give you an idea of why type classes are very powerful, you can have a type class that is defined in some third-party library. You can have a value object that is defined in another third-party library. You can define this instance, implicit object person serializable, extends serializable of person, and say how person should be serialized. So the key thing to remember about type classes when you start reading about them is the type class itself does not know about these instances, and the class for which you're defining this instance, they also don't know about these instances. So the only person who knows about these instances is what we do within the instance itself. But you get some tremendous benefits like we just saw. You can piggyback, when I want to do something like lift, I can piggyback on the lift that is defined in the functor type class. And the reason we're able to do this is functor is fully parametric. Function cannot do anything fundamentally unsafe because it has very, very limited knowledge of what it is working with. It doesn't know what f is, it doesn't know what a is. So that is the constraints we are talking about. That's, I think, sort of the point of this presentation. So is that clear how type classes are different from inheritance and sort of benefits that they get? It's a classic example. The serializable is what you would find when you look to online presentations for type classes. So just going back to our presentation. So functor is just an example that I lifted from some open source libraries for Scala. There are many other like this, functor, applicative, monad, traverse. So how many of you know of this optional type in Java 8? Optional, maybe, option. So what it is that in Java 8, what it says is basically it is to indicate an option, absence of a value. So you can have an optional of some value, or you can have no value, which is denoted by some type called none in Java 8. I'm not sure what Java 8 calls it. In Scala, it's called none basically. None is a type that indicates the absence of a value, whereas sum of some value indicates the presence of a value. So just to sort of give you a very simple idea of how powerful this notion of type classes and higher kind of types is. A couple of weeks back, I was working with some code where I had a list of option in my hand. I had a list that within which there were many optional values. So I don't know anything about them. Some of these could be none where they have no values. Some of this could have some values, some useful value that I want to work with. What I wanted as output was option of list. Basically what I wanted was if all these values within the list had useful values, I wanted all those values to be put together in a list and it to be wrapped around an option. So that's making sense. So I had a list of option of, let's say, string. And this could be, let's say, a list of sum of a, could have a none in there, maybe it could be a sum of b. So this is just a list that has 3 optional values, where 2 actually have useful values in them, 1 is none. It does not have any useful value that I can work with. What I wanted as output was an option of list of string, right? So which in this case would evaluate to none because one of the inner values is none. In this case, since one of the inner values is none, the final output of my transformation would be none. Whereas if, say, instead of this none, well, let me just remove that none, what I would have here is a sum of list of A, B. So this is what I wanted when I was working with some block of code. So in Scala, this is it requires a lot of boilerplate to do. I'll have to write for comprehensions. I would have to go into the list, then go into the option within the list, inspect every value, put them all together in a list, wrap it in an option, and return it. It's definitely doable. It is not even a lot of work to do it, but it's just boilerplate that I don't want to write. Whereas because of this power of type classes and higher kind of types that we just saw, in the Scala Z library or in the catch library, in the applicative type class, there is a function that does just this. It's called sequence. And the beauty of that function is that function is not defined for list, it is not defined for option, it is not defined for any other type, it is defined for any f and any g. You could take a list of option, convert it to an option of list, you could do vice versa. You could have another type of yours in the future that is an f, and you can do it for that also, so long as you have an applicative instance for it, just like we saw now. So in the functor example, in the future, if I wanted to create a new type for which I had a functor instance, I get access to all the useful functions defined within functor itself, like lift, which we just saw. So that is, I would say that is the power that you get with higher kind of type classes, and the constraints that these two concepts impose on any code that we write. Yeah, so this may look, for people who are new to Scala or to these two concepts, it may look very kind of Greek and Latin to you if it's the first time you're being introduced to them. But once you spot, it's like inheritance. Maybe the first time you saw inheritance, you just say, okay, what am I doing? This extends something, I don't know what it means. It's like that. First time it may look weird, but once you start spotting opportunities where you can create type classes, it is, I think, very, very powerful. And like I said, in 20 years from now, if I have a functor type class and I wanted to create an instance for it, that instance would be valid. And again, you get compile time benefits which you don't get when you're doing normal inheritance, where you can do casting, where there's dynamic dispatch going on, things can fail at runtime. Whereas this is all verified at compile time. If I want a functor of something or if you want an instance of a type class, it has to be there at compile time. The compiler will search whether it exists. If it doesn't exist, it will fail. I have to give it that instance. So yeah, finally going to conclusion. So I think the first example what I was going for is code we write is always constrained. I think that's one of the key concepts that I wanted to come out of this presentation, is that any code that we write is always constrained. So how many of you have done this? You've written a block of code, come back 2 days later and it doesn't make sense to you.
Come back after tea, it doesn't make sense.
Sorry. Yeah. So, and the reason for this is when we write that block of code, we have some mental model in our head, and we always have to make it explicit. So you can do this with tests, obviously. That is what we do in test-driven development. In test-driven development, we say these are the constraints that I want in my code. You encode them as tests, and you use them as specifications. You do documentation for it. Since I am a fan of type theory, I would like to use types for it. The fundamental point is we have to make these constraints explicit in our code. We have different tools for doing this. In this presentation, we just saw some of the tools, that's all. Making them explicit always makes it easier to read and understand our code. The more constrained our code, the more easy to read and refactor it is. I think that's something most of us can agree with. And being a fan of type theory and functional programming, I would say parametricity is the bare minimum constraint we should be working with, or at least types. If you don't have either of these, I would say that at least try to make your code immutable. Try to use them as constraints to limit in what you can express about your code. If your language supports type classes like Scala does, like Haskell does, like a few other languages does, you can mimic type classes in Java also, though it is kind of difficult and boilerplate, you can still do it. You can look at the functional Java library for examples. You must prefer type classes. Higher candidate types enable a lot of reuse, which we just saw. So higher candidate types are one of those concepts that once you're used to it, it is very, very difficult to go back. So if in the list of option case, if I were working in a language that didn't have higher candidate types, I would have to write that once for list of option, I would have to write that once for option of list, I would have to write that once for some other two types that needed to be combined. And I had to define it once for every type of every combination of types that I wanted to be combined. Whereas with higher candidate types, we can put them all in one bucket and say this is how I want any two F and G's to be combined. That is the power you get with higher candidate types. And I think the key sort of concept I was going for with this presentation is we should always be reaching for the most constrained abstraction given the language we are working with. In a dynamically typed language where you don't have types, that would be immutability and pure functions and a few other concepts. In a typed language, it would be types. in a parametric language, it would be parametricity. And when you have this full power of the type system, you use it to really constrain what you can express in a single block of code. Two presentations, and the last is the paper. Thank you. I think, do we have time for questions rather than with names? That is the whole point that functional programmers are aiming for, I guess. Names do matter, yeah, I agree.
So beyond what is available in Scala, higher kind of types. So you do Haskell also. What is in Haskell that is not in Scala? Beyond the concept of a higher kind of type. Because in Haskell, I know you can't mix pure and impure functions.
Yeah, you can't do that.
But and higher kind of types, that concept has come from Haskell, basically down to other languages.
Yeah.
Apart from that, are there any other concepts in Haskell or other programming languages like Idris which have not flown down to the more well-known languages like Scala?
Yeah. Haskell, I'm not sure. I think a lot of things you can do in Haskell, you can do in Scala. I've not really delved very deeply into Haskell to really say that something you can do in Haskell that you can't do in Scala. And the way Scala encodes type classes, people find it to be better because in Haskell a type class is like global. If the same example, if in Haskell it were searching for a functor of list, there would be one functor of list in the entire Haskell language. There is no scope for type classes in Haskell, whereas here you have implicit. So you have implicit scope. You can mix and match various type classes together. So people find this to be one of the things that Scala, and probably the only thing that does Scala does better than Haskell. But Idris, I think I was just learning it over the past weekend. We have this notion of dependent types that I think. So it's funny because when I was going through this presentation in my head, when we came to the slide of parametricity, what I wanted to say was, in 2016, we are talking about a paper that was written in 1989. So it's like 30 years, and we are now only sort of trying to comprehend the concepts of something that was written 30 years ago. So dependent types is a fairly new concept that is there in Idris. By the time we use it, I think we'll all be very old. By the time it reaches the industry, at least I guess, we would be like 20 years down the line. But it's very, very powerful where you have types that are dependent on values. I think that is something you can mimic in not the entire power, but you can do something similar in Scala. I think using a library called Shapeless. I haven't really played with it. There's a presentation where these two people compare Idris and Scala Shapeless. And Idris is in Scala Shapeless. If you were to do it like 20 lines of Scala code is equal to 1 line of Idris code. That is how the presentation sort of appears. Idris is very, very expressive. But by the time it ever reaches adoption in the industry, it would be like too late, I guess. Unfortunately. So, any other questions?
Using a programming language is for specific problem solving, or can I use database and say it's a pure function?
Yeah.
Meaning, if I use a database, so I can just send an update. So, meaning state of the object has changed.
Yeah.
When I started meaning pure function is basically I give the same variable again and again, I get the same result again, and the state of the object or nothing changes.
Yeah.
But when you put a database inside, the state changes, right? So I don't think so. Functional programming is a better type.
So I think that is sort of the misconception that most people have. The goal of functional programming, specifically with types, is for us to express what this block of code do rather than do it. So in the case of database example,
one goal of whatever functional programming. What I'm saying is when you take a functional programming, it's basically a pure function.
Yeah.
Whatever I give, I get. The type classes, the additional thing you get out of functional programming. Like say C is a I don't know, C is a functional programming? No.
Imperative.
What is it?
Imperative.
So when you say pure functions, and then when you put a database inside,
yeah, so
will it
you don't have to all write pure functions all the time. Okay. So in F#, which is basically for the .NET stuff, you have a lot of functionality. Basically, the entire framework is available to you. Plus, on top of that, they have type providers. This is a very interesting concept. This is basically something like your entity framework, but without all the EDMX and all that.